Hello. I wanted to make a short video on the comparison between LSTM and Transformer Encoder for a problem that I'm very interested in, which is protein classification. And I selected this problem because the protein language of amino acids is only usually about 30 elements in size versus a natural language problem where English or some other language is used and the number of elements is far larger. And so with this reduced dictionary size, it's possible to achieve strong learning with a very simple model. But I wanted to do this comparison because the transformer encoder, even one transformer encoder layer, seemed like it was maybe overkill for the problem. So I wanted to use a more traditional approach like LSTM and see how the two compared. And how I set this up is I wanted to keep as much the same between the two models as possible. So I kept the exact same input embedding, positional encoding steps, and then after the language component I kept a conv1d dimensionality reduction step and classification layers. And so the only thing that I changed between the two was the language component, a transformer encoder layer versus an LSTM layer. And so just to further talk about this, I only changed this one layer, and the dimensions are preserved across both layers. So our dimensions of batch size, sequence length, and embedding size coming out of the positional encoding step pass through each layer, and those dimensions are preserved for both methods. And so I also wanted to keep as many of the hyperparameters the same as possible. This might kind of bias the experiment a little bit if I did hyperparameter tuning for each specific model and tried to find the best parameters. It's possible that my results change a little bit, but I wanted to get as straightforward a comparison as possible, and these numbers worked very well for the transformer encoder when I used that model in a previous video. So I just kept all the parameters the same with the exception of a varying embedding size to try to test different sizes of models across both approaches. And so on the next slide I'll show the results of that experiment. So in terms of a comparison between the two, I thought about just doing straightforward accuracy, but I wanted to also include the training time because in the textbook approaches to natural language processing, it's often cited that the transformer and self-attention in general is so revolutionary because it speeds up training immensely compared to a recurrent network where you have to loop over items one by one. And so, as we can see here, with the smaller embedding sizes, the LSTM network actually outperforms the transformer in terms of accuracy. And I thought this was very interesting and maybe points to the fact that the transformer is too complex a model for this problem. However, I just wanted to also note that if you scale up the embedding size, the transformer training time does not increase significantly. So we can get higher accuracy out of the transformer, and even the best accuracy found in the experiments was with this 512 embedding size transformer. But the time it takes to train that is relatively similar. Whereas by the time I reached 256 embedding size for the LSTM, it took almost an entire day to train, and the accuracy was very, very good, but this is just not feasible in terms of a training time. And so for this simple problem, maybe the LSTM is the better approach just because you can use a smaller model and achieve very good results. However, when you're embedding something like the English language or a large natural language problem, I think this really speaks to why the transformer is the state of the art and why larger and larger transformers are becoming the norm in the industry. And so I just wanted to share these results and have a quick couple slides on this. I'm definitely going to switch topics for the next couple of videos, but until then, I thank you very much for listening and appreciate your time. Thank you.